Hello everyone, Aaron here. Welcome back to Leetcode. Let's jump right in and see what today's problem is. Spiral matrix 2. Let's have a look. So, given a positive integer n, generate an n by n matrix filled with elements from 1 to n squared in spiral order. 1, 2, 3, 4, 4. Okay, that makes sense. So in the reduced case, we've got 1. Oh boy, this is going to be interesting, isn't it? I don't think. So my gut instinct is there's not a recursive solution going on here. There's no sort of smaller submatrix that's going to help us. Although, having said that, what we've got here is the matrix in the middle is 1, 2, 3, 4, 5, 6, well, starting 8 further than the one we've got. Although that's probably going to be an absolute pain to try and extend, isn't it? I don't know. Let's jump in and have a bit of a play and see what happens. Alright, generate matrix. Well, we know exactly how large the matrix is going to be. So we can create a new array of size. In fact, no, let's not do that. Let's do it this way. I might even do this slightly differently. Rather than doing a standard loop, I'm going to start from 1. No, I'll get myself confused if I try and do anything too fancy. So let's do it the old-fashioned way. Right. So we now have our indexes into this array. Every particular cell, can we associate its value with its indices in some way? Well, 0, 0 is always going to be 1. So the first row is always given by j plus 1. Second row is, oh gosh, this is quite awful actually. The easiest thing to do would be to just build the empty matrix. You know what, let's start there. Let's build the empty matrix, and then just start spiraling. So what this does is it gives us an empty a matrix filled with zeros, effectively. And then we've got to work out how we're going to traverse this thing. How do we want to traverse this? Let's do dj and di. I varies down, j varies across. K equals 1. So the thinking here is that k is going to be what we're filling in, but what we want to do is for, you can do this in here, k equals 1, k is less than n, less than or equal to n times n, k plus plus. Basically, what we want to do somehow control the traversal. So it's the result I j gets filled with k, I plus equals di, j plus equals dj. But then the trick becomes, how do we want to actually know when to turn? If I is equal, actually this check should be done first. If I equals the upper bound, in fact, I'm going to do this the other way around first, just because it's the way I'm thinking. So if we're going across and j is reached the upper bound, then dj equals 0, di equals 1. Else if j has reached the lower bound, should call these j upper bound, j lower bound, then dj is still equal to 0, but di now is going in the other direction. In fact, no, we need more than this. Oh gosh, how do we detect? Because here, no, I think I want to do this after the check. If j has reached the upper bound, so it's here. No, in fact, if it's got to here, then that's what I want to change. dj does not equal 0. dj does not equal 0. Just yeah, I think that's the way I want to do it. So if I've got to the end, but I was varying j, then that's what I want to do. So now I want to do the same thing with I upper bound and di does not equal 0. Di is now 0. dj is 1. So we've reached the upper bound. Oh, actually, no. J wants to be -1, doesn't it? Because we've got all the way to the bottom, we want to walk that way. Top. Yeah, I think that's correct. Else if I is equal to I lower bound and di does not equal 0. di is now 0, dj equals 1. We got all the way to the top and we're going across. Perfect. So I lower bound equals 0. Let I upper bound equals n-1. Let j lower bound equals 0. Let j lower bound upper bound n-1. So now the trick is, how do we change these bounds? What we want to do is that if j has progressed all the way across, well, that's all right, because we want to walk all the way back, but we do want to set i's upper bound, i's lower bound 1 lower. And when we get to the bottom, that's where we want to set j's upper bound. And then when we walk all the way back, that means we can't walk down any further, so that's when we want to set i's upper bound gets one lower, and then finally this is when we've walked no, that was yeah, so when we walked all the way up, that's when we want to set j's lower bound. One higher. Oof, that's a bit of a nightmare, that code. And then finally return the result. And after all, in our case, k is handled. Oof, absolute nightmare. Right, let's have a go, shall we? So we've built. Let's pull that out. Just because it's tidier to have this pulled out. Okay, so I and j. No, I've got myself confused. This is ridiculous. All right. Let's test this out ourselves first. So we've got k, I, j, di, and dj. So k starts at 1, and we're writing that in position 0, 0, and the current deltas are 0 and 1. We move to the next spot. K is 2. And then what we're going to do is we're going to have I plus di, that's still 0, j plus dj, that's a 1. Di, we're not in any particular edge case, because although we're at i's lower bound, we're not with delta I is equal to 0. So we've got no particular edge case there, so that all stays the same. K is now 3, we're at 0, we put 2. 0 and 2, that is j's upper bound, and dj is not 0. So now we're going to get dj is 0, but di is 1. 0. So now k is 4. We're going to be writing it 1, 2, 1, 2. That's good. Actually, I'm going to put in more information here. Upper I, lower I, upper j, lower j. So here it was 2, 0, 2, 0, 2, 0, 2, 0. And then what happened here was we went to 1, 0. I's lower bound, oops, that's increased by 1. So that went to 2, 1. But y didn't change. This is 4. So here we've got k is 4. We're writing in position 1, 2. We're at i's lower bound, and di is not 0. Oh, that's a bug. We've hit this case. I is equal to i's upper bound. Sorry, I is equal to i's lower bound, which it is. that would say that we're going to set it like this. But that's not what we want. That's not what we want at all. So this should actually be checking whether we're moving in the right direction. Not that we're moving, but that we're actually moving where we expect to be. So if we make that change, now we don't do that. We're at 4, 1, 2. So J is 2. So di is the one that's, di is equal to 1. That's that case there. Is I at its upper bound? I is not at its upper bound, so we're going to continue not making any particular changes. So that's going to be a 1, 0, 2, 1, 2, 0. So now we're at 5. I goes to 2, 2. So now I is at its upper bound, and di is equal to 1. So we're going to get di is equal to 0, dj is equal to -1. dj's upper bound, and j's upper bound goes down by 1. So that all stays the same. Right, we're on round 6. That stays the same. And we wrote in the previous place, that's a 6, 2, 1. So that's that one there. That's correct. Are we in any particular case? dj is -1. J is equal to j's lower bound. It isn't, so we can carry on unchanged. 7. We've got 2, 0. 2, yes, that's what we want to see. Now we've got dj is -1 and j is at its lower bound. So dj, so di is -1, dj is 0. I's upper bound is going to decrease and the rest are going to stay the same. 8. What's going to happen? We're going to go to 1, 0. That looks promising. So we've got di is -1 and I is at its lower bound. So di is going to go to 0, dj is going to go to 1, and dj's lower bound is coming up. We're now at 9. We've got a dj, so we're at 1, 1, 1, 1, perfect. This is the final loop of k. So we're in the case where dj is equal to 1. Is j at its upper bound? It is. So we're going to get a 1, 0, and that's i's lower bound is going to come up, and then we're done. Okay, that looks like it works. Holy moly, that's rather complicated, isn't it? Don't love this, but I could stick it in objects, but at the end of the day we've got the same number of parameters we're keeping track of, or sorry, same number of variables that we're keeping track of. Ooh, I think it's going to be difficult no matter what we do. I say we give this a little test run and see what happens. Can't hurt, can it? Alright, so I'd like that one. Let's throw in the extra test case here of 1 and see what happens. Do we just get the singleton 1? These kind of edge cases are always an absolute nightmare. We do. Alright. Feeling bold? Let's submit it. All right, we did pretty good. We were pretty damn good on speed. We bet 3/4 of the other submissions. Didn't do so good on the memory. We used quite a bit of memory. I suspect it's building that empty. Well, no. I don't know why we were so bad on memory. Just have a few too many variables, I guess. Don't know which one we want to cut though. You could probably decompose K or produce K from I and J, but I'm happy with that. So thank you very much for watching, and I will see all of you tomorrow. Bye.
2 hours later.
All right, I couldn't help myself. I'm having another go, and we're going to try and do this using a recursive solution. So let's immediately just use a little helper here because I'm going to need an extra parameter. And what it's going to take is a n as well. It's going to be a number. And we're going to do an offset. How far are we starting from 1, effectively? Or actually, no, not start. An offset, just to start. And the idea is if n is equal to 1, and I just want to return the start in a little matrix by itself. Otherwise, what I want to do is I'm going to get a smaller matrix. So we're going to make it n-1 sized, but the start is going to start at, well, because this was a 3 by 3, it's going to start at 9. If this was a, well, basically what it's going to do, it's going to do 1, 2, 2n minus another 2 lots of n minus 1. Hang on. So hang on, if we've got start minus 2n minus 2n minus 1, that's the same as start minus 2n minus 2n minus 2. That's the same as start minus 4n minus 2. So let's simplify that a little bit. Just for my own sanity. So this gives us effectively the little inner core here. And then what we want to do is the top row is going to be, effectively it's going to be the numbers from 1 through to n. And then we kind of want to do the same thing for the bottom row. But rather than going from the start up to start plus n, what we want to do is we want to start at, what do we want to start at? So that's going to be start plus n plus n minus 1 plus I guess. Guess we'll find out when we get going as to whether that's correct or not. Oh, hang on. I think there's a mistake here because this inner spiral, what does it look like if we go one larger? 1, 2, 3, 4. Something, something, something. 5, 6, 7, 8, 9, A, B, C, D, E, F, G. Oh no, that's still a correct spiral. The problem is, if n is even, we've got a much trickier job, don't we? Because if we've got 1, 2, 4, 3. Because here we don't actually want to go. We want to go too smaller every time. Yeah, so hang on. If n is equal to 0, what do I want? I think I just want an empty array. It's not an edge case we have to worry about in the problem specification, but I think it's an edge case we have to worry about in the recursive solution. Yeah, I think that's right. Or I might handle the case of n equals 2 actually. N is equal to 2. Return to list start plus 1, start plus 3, start plus 2. I think that's easy enough, and I think it's a slightly easier base case to worry about. So now what I want to do is I want to go to inner for each row. Can't remember the exact syntax for this. What I want to do, I think you can also ask for the index here. So when I'm 1 down, I want to add on to the end if I'm in I equals 0. I want to do start plus n plus I plus 1, I guess. 1. Oh, no, I don't want plus 1. God, there might be a whole lot of plus 1 errors around the place here that I've got a problem with. Because that one there, if we're starting at 1, I'll come back to that. And then what I want to do is I want to work at start plus 2n plus, because that's 1 that way, 1 that way, plus n minus 2 plus another n minus 2 minus I. Ugh. 2, 3, that's 4 n's minus 4. Oh boy, the maths on this one's going to be a bit fun. Basically what that does is it shifts, and then I want to return top row, the inner, and the bottom row. I think that spread syntax is valid. Now I don't want that anymore. So let's have a go with 1. If it's 1, I'm just going to get 1. If it's 2, I'm going to get 1, 2, 4, 3. That's correct. If it's 3, what I'm going to get is, well, I'm going to ask for the size 1, and I'm going to make that start at 1. What is that? 1 plus minus. Oh god, no! I've done a horrible thing here. This is terrible. I don't want to do minus 4n. I think I want to do plus 4n minus 2, because I want to do 1 plus 12 minus 2. No, I don't. What do I want to do here? Hang on. So if I want starting at 1, I want to do the inner one. I want to do 2n. Start plus 2n plus 2n minus 1. That is 4n minus. But it's not minus 2, is it? It's minus 4. So that should work better. So now I want to do 3 4s are 12 minus 4. That's more what I'm after. So then what happens is we go in here. So it was 3, it's now 1, and we're going to start at 9. So that's going to give me a 9 center. The top is going to be 1 plus 0. It's 1 plus 2. So the top is going to get 1, 2, 3. The bottom row is going to get me start plus 1 plus 6 minus 1. Oh, why have I got the minus 1 there? That's what it is. So I want to go done. All of those and all of those. It's going to be what? 2n plus n minus 1. And then it's going to be, well, that's the 7, 6, 5. And then I want to minus the I, minus 0. So is that correct? That's 2. And so that's going to be 6 plus 3 minus 1. 0, 1, 2. No, that's not correct. Again, that's an n minus 2. That's a 3n minus 2 minus I. And then in the middle of each one, so here I'm actually looking at I equals 1. So I've got 1 plus 3. Start is 1 plus 3. Oh god, hang on, have I got that right up here? Oh, it's a different one. 1 plus 3 plus 1 plus 3 plus, in this case, 0. That's 4. Well, that seems to work. And then 1. Oh, that's all we're getting. But then at the start, I want to do 1 plus 12 minus 4 minus 0. Nope, that's not correct. That's a 9, but I wanted an 8. So what do I actually want? I want to do 1, 2, 1, 2, 2n plus 2 lots of n minus 2's, 2 to 2. That gets me those, that gets me there. And yeah, then I want to subtract the I, so that's 4n minus 4. Oh no, that's correct. But I guess there's a minus 1 offset there because of the start. Oh god. start at 1. Yeah, I think it's a -1 there. So hang on, why does this work? It's because I starts at 0. Does this one work? We've got 1 plus 3 3s are 9 minus 2 0. So that's going to be no, it's not. We need the -1 offset there as well. Okay. Alright, let's have a quick test of that. Not so confident in it, but we'll see. It seems to work there. Now, JavaScript isn't great at recursion, but we'll give it a go. It's probably going to score very badly, but it's a bit of a tidier solution in one sense and a bit of a grosser solution in another sense. So we'll see how it goes. I don't expect it will be very good for either time or memory. Time improved. Memory stayed completely identical. Not sure why memory stayed completely identical. And I think that that time is well within standard error of measurement. Okay. Well, there's 2 ways to solve today's Leetcode problem. Thank you very much for watching, and I will see you tomorrow. Bye! That's a bit of a nightmare.